Hi, my name is Cristian Stanciu. I'm from Politehnica of Bucharest in Romania, and my host for this fellowship was CERT. And today I'm gonna present to you my progress in the defect detection using capsule networks and different temporal approaches. So I'd like to start with an overview. Um, uh, for this approach, our main goal was to find new solution for the defect detection problem. And when detecting defects, generalization is the most important thing. So we already have a lot of architectures that can provide 99% accuracy, but across data sets, different data sets, it is not like that. My solution is based on capsule networks, and the main question of this fellowship was, can capsule networks be used to at the video level? Okay, so first of all, let me start with a little introduction. Uh, Image generators are getting much better, and deepfakes are becoming more realistic. And although there's very much progress in the defect detection algorithms, the majority of them are at image level. And also, although the results are good, we are still dealing with generalization. So the defects can be created in many ways with many architectures, and we can train on some of those and get them perfectly. But then in the real world, it's another story. So we need to generalize better. So for this, we have a starting point, which is my capsule network architecture, which I presented in the Multimedia Against Disinformation workshop. And this particular architecture got some impressive results using a small number of parameters. So 99% area under curve on two data sets, phase for index and celeb. But when trying generalization across data sets, so training with phase forensics and texting with celeb and the other way around, the area under curve was like 70%. So the question is, how can we generalize better? Okay, so like I said, the biggest problem right now in defect detection is generalization. And one of the best ways to generalize is to use temporal approaches. Why? Because while the architectures might have some fingerprints on image level, those can be hidden, can be erased, or can never be learned. So that's why we try to use temporal approaches, because if we use a temporal approach, then we only want to see the evolution in time. The most basic approach, of course, is to average the outputs of a neural network for every frame. So our question was, can capsule networks work at video level? Can we pass multiple frames onto capsule networks and obtain better results than just averaging the output of every frame? Okay, I'm gonna make a short introduction of capsule networks for those of you who do not know. So basically, this is my basic capsule network architecture. It starts with a 2D CNN, and with convolutions, we get with convolutions and reshaping, we get some vectors of length 8, and those are the primary capsules. In this case, we have 7200 primary capsules. The job of the primary capsules is to try to figure out what the output in the secondary capsules will be. So they're trying to guess the output. They do that by we multiply the 8-dimensional vector with an 8 by 16 matrix. So we get a 16-dimensional vector, and then we use all the primary capsules in a weighted sum to guess the output from the secondary capsules, which are fewer in number. This weighted sum is computed with a dynamic routing algorithm, and that algorithm is kind of similar with a k-means algorithm, kind of. The secondary capsules go then into a fully connected layer, and they output a prediction of DeepFake or not. Okay, so then we wanted to start from this architecture, this approach, and see what can we do to pass multiple frames to a capsule network and get some good results. So we have groups of consecutive frames which go into a backbone. The backbone can be basically any neural network. So it can be a 2D CNN. It can be a 2D CNN with capsules. It can be a 3D CNN for groups of frames, and so on. We output some feature vectors or capsules, and these feature vectors form primary capsules and go into the second capsule network, which is the capsule network for the time dimension. I'm gonna take these elements one by one and explain what they do. So first of all, the backbone is used to extract features from images or groups of images. In our experiments, it was a 2D CNN, like exceptional or VGG19, plus some capsule networks to output some capsules. We also used a lot of 3D CNN on consecutive groups of frames, and then we used capsules or 2D CNN and then capsules. For the time capsules, we take the output from the backbone, and we try to compose a weighted sum of those newly formed capsules to form the secondary capsules. This configuration can vary a lot. We can stack those capsules. We can use them as a single capsule. We can have different lengths. We can add positional encoding, so like a transformer, or we can add an encoding for the meaning of the capsule, because the capsules in the same position can have the same meaning. This is our architecture. So basically, we use a 3D CNN, or one of our architectures. We use a 3D CNN on groups of eight consecutive frames, and we do no average pooling on the spatial dimension, and then we go to a 2D CNN and capsules. The result are one group of capsules for each group of 8 frames. We stack those, and we also add positional encoding, so that we know which type of position each capsule has. Unfortunately, the results do not match state-of-the-art approaches. The base state-of-the-art approach used transformers and train on Faith plus, and was evaluated on CLFDF and got an 86% area under curve. But as with any other experiments, we got a lot of useful insights on why those do not work. So basically, our best architecture, the one I presented, was just slightly better than just averaging the output of the images. One important insight when comparing with this architecture which use transformers is that transformers use attention, and that can be applied to capsules, and that is something very good for future work. Attention capsules have already been implemented in some way, and that could be the key to make capsules much better in the temporal dimension. As some conclusions, after experiments, unfortunately, our results were not as good as the state of the art, but we learned some important lessons, like the fact that capsules do not work well in the temporal dimension with their basic form, but they might work better with attention. It is also an important conclusion that video level methods are very important to generalization, and that defect detection should be predicated on video level methods, and also this junior fellow program helped to strengthen the collaboration between CERT and UPB, and we are collaborating further in implementing other temporal approaches. Thank you.